Now we're good. Do I need to stand closer? It's fine. All right, y'all. Welcome to the Compass Lecture Series. If you haven't already signed in, we encourage you to do so either now or at the end of the talk. We do this every Friday, and hopefully we usually have a good lineup of speakers still to come. So please continue to come back. There's team cookies in the back, all that. But it's my pleasure today to introduce one of my friends and colleagues from my alma mater, Michigan State University, but now a graduate student at UC Berkeley with me. He did his undergrad degree there. Neel, sorry, I didn't say his name, was that Modi? Did his undergrad degree at Michigan State, and I remember I ran into him for the first time when we were both taking E&M2. And when is that echoing? Okay. We were both taking E&M2 and sitting in this class, and I was talking to this kid, and he was so smart, and I was just thinking to myself, like, man, I'd love to do a project with this guy, but then COVID canceled our project. So unfortunately, we graduated alone, but at the same point, it was still a good time. And I think I was shocked when I figured out that he was both a good physicist, he was a good mathematician, and he was only in his second year, and we were graduating at the same time when I was in fourth year. Pretty cool. Then after that, Neel went to Perimeter for 2 years, right? Or 1 year?
1 year.
1 year, sorry, my bad. So, that makes more sense, yeah, because we both graduated. I came here, you went to Perimeter for a year, and so you studied condensed matter and, you studied condensed matter and machine learning at MSU, but then at Perimeter, did you also study the same thing? You studied, here we go, that's in your bio, research related to spin foams and random tensor networks. I don't know what those are, but understandably, you do apparently. And then since then, has come to Berkeley and is now in your second year working on quantum signal processing and for stimulating quantum field theories, which is super important in the world of quantum computing and just understanding our quantum regime in general. I'm sorry, I already asked the name and I already forgot. It's Christopher Bauer.
It's Christian Bauer.
Christian Bauer, my apologies. Christian Bauer up at LBNL. Yeah. So I'm really excited to hear Neel's talk because I'm a good teacher and explainer. So I wish everyone to welcome Neel, and we give it to you.
Thanks. Okay, so the goal of this talk technically is going to be to calculate one specific integral. Now, technically, the calculation of this integral is not specifically part of my research, but in general, my research involves calculating similar types of integrals. And for this particular method of calculating this integral, I'm going to be following a paper, which is by Kyle Poland, Christian Beer, and Tobias Osborne from 2020. And in the paper, they credit these two people, R.M. Haar and Matt Hastings, with some of the ideas involved in calculating this integral in a way that is relatively simple compared to some calculations you might find elsewhere in physics. The title of the paper is called "No Free Lunch for Quantum Machine Learning," and that gives you a sense of what the paper is about. But we're not going to actually be going into that. We're just going to be going through the calculation of one specific integral in a really interesting and elegant way. So, without any context, I'm just gonna tell you what the integral exactly is, what it looks like. This is what we're going to be calculating. So I don't expect you to understand what this means at the moment. We're gonna carefully define what these things mean. The diagrammatic notation. The only thing that hopefully you're familiar with is the integral symbol, and that's basically something that comes from calculus. So to start off, well, okay. So I think in the blurb for this talk I mentioned that we only need the fundamentals of calculus, but we also need a little bit of linear algebra. So I guess I lied a little bit, but we'll go through both of the parts. So to begin, I'm going to start by talking about something that seems completely unrelated to quantum circuits or integrals and all of that. I'm going to start by talking about clocks. So imagine a clock. A clock is a circle of numbers. For instance, take the clock on the left. That's an actual clock. The 12 is at the top, the 6 is at the bottom, and you have the numbers from 1 through 12 going clockwise. But now take the clock on the right side. So that clock has a 1 at the top and a 7 at the bottom. It's not the same as the clock on the left side. However, there's one important property of both clocks that is the same, and that is the sum of all the numbers around the clock. And that observation in calculus can be made slightly more general. Instead of having a clock with a finite number of numbers, imagine that you have a circle, an entire circle, like in red over here. And imagine that you have a function that's defined on that circle. Now, points on the circle can be labeled by an angle theta that they make with the horizontal. The value of a function can then be specified by essentially plugging in some number for each value theta. We denote this by f of theta here. And so basically the shape of the function is this kind of black curve here. So the analogous statement to what we had with the clocks is that if we integrate the function around the circle, that is integrating it from 0 to 2 pi, that resulting value is the same as integrating the function, but plugging in theta plus some constant a. So so adding the constant a essentially it basically amounts to a rotation by some angle a. But because we're integrating around the same circle, if we just rotate the graph of the function by some angle, the total integral, like around the whole circle, won't change. So if this is a little bit mysterious, and if you're not familiar with integrating functions over circles, what you can imagine instead is you can consider the integral of some function f of x dx over all real numbers, and a similar thing happens there, where the integral of some function across the entire real line is the same thing as integrating that function, but replacing the argument with x plus a, so translating it by a bit. And you can see this, for instance, by doing a u substitution and setting u equals x plus a. But now, at this point, I want to make a change of notation. So we've been denoting points on the circle by an angle theta. Instead of doing that, we can it's possible to denote points on the circle by a complex number of the form e to the I theta if the angle that the point makes is theta. And I'll basically denote those kinds of numbers as u. So instead of having a function which is now which previously was a function of theta, that can be translated into a function now of u, where u is this complex phase. I guess the terminology is that a complex number with unit magnitude is called a phase. At this point, you can notice something interesting, which is you can actually rewrite the integral from before, the integral of f of theta d theta from 0 to 2 pi, in terms of u. Now, the notation for this is the bottom line here, the integral du f of u. And we simply define this to be equal to the integral d theta of f of theta from before. If we go ahead and do this, then what we can imagine is the previous situation that we had, where we can translate the angle by theta, or in general, we can translate the angle by a. That basically turns into, in this particular notation, we can multiply u inside the argument of f by an arbitrary phase v. And so that gives us this equation down here. Now, at this point, you might be saying, wait a second, but isn't there something called the u substitution in calculus, where if you want to change variables from theta to u, you have to set u equal to e to the I theta. You need to calculate what the du is in terms of d theta, plug that back in, and that won't give it, and that's not going to give the same thing, because you're going to have an extra factor of whatever the derivative of e to the I theta is. And you'd be right, but the interpretation here is actually different. So if you notice, when we're integrating a function of theta, the meaning of the integral, if you recall what the definition of the integral is, what we're basically doing is we're taking samples of the function, we're multiplying them by small changes in the angle, by small differences of the angle, and we're adding those all together. But here, what we're doing in this notation is actually something entirely different. Instead of taking small changes in, instead of taking small differences in the value of u in this phase, in this point on the circle, we're taking ratios, small infinitesimal ratios of nearby points on the circle. And so instead of just adding everything together, There we go.
See how it should fix now.
Can you hear me now?
Try again.
Okay, awesome.
Cool.
Okay, so this is so here we basically have two different notations. Actually, there's three notations here. If you notice closely, there's the actual entries of the matrix. There's the indices, and then there's just M without any indices at all. And we just sort of imagine that there are indices in principle that exist. So I'm going to start off by basically speeding through some operations that you can do on a matrix. The first operation I want to go through is the transpose. The transpose of a matrix is defined basically to be the matrix where you take the entries and you essentially flip the entire set of numbers along the diagonal. So for instance, 1 plus I stays in the same spot, 4 stays in the same spot, but 3 and 2 minus I gets switched. In terms of the component notation, that would be M transpose subscript ij equals M subscript ji. So we're just flipping the order of the rows and the columns. And there's another important operation, which is that of the complex conjugate of a matrix. So all that is just taking the complex conjugate of each entry of the matrix. So originally we had 1 plus I, 3, 2 minus I, and 4, becomes 1 minus I, 3, 2 plus I, and 4. We can denote that in terms of the indices like this. So M conjugate, the ijth entry is the same as the ijth entry of M complex conjugated. Okay, and then we can put these together, and that gives us what's called the Hermitian conjugate of the matrix M. That's the complex conjugate transpose. And in terms of the components, or in terms of the entries, you can similarly see this relation over here. At this point, I should mention an important. We'll get back to this at a later point. So there's two important classes of matrices that we want to talk about. The reason that we talk about these matrices is because they're really relevant for quantum mechanics. I won't get into all the details at the moment, but the two classes of matrices that we're going to be really interested in are so-called Hermitian matrices and unitary matrices. Hermitian matrices are matrices H that satisfy the property that H dagger, that's what the symbol there is called, is equal to H. So the Hermitian conjugate, or the complex conjugate transpose of H, is equal to itself. And a unitary matrix is a matrix U that has the property that if you take U dagger times U, that equals U times U dagger, and that equals the identity matrix. And we're still working with n by n matrices in principle, even though the examples I've given so far are 2 by 2 matrices. Given a matrix, you can also calculate its matrix exponential. If you have a matrix M, its exponential is denoted as e to the power of M, and it's defined to be the Taylor series of the exponential function with the matrix plugged in. An important fact is that if you have a Hermitian matrix, for instance, H, and you take the exponential of I times H, that is a unitary matrix. And this fact will come back later. Okay, so now we've exhausted pretty much all the functions of a single matrix that I wanted to define. So let's go on to functions of multiple matrices. The simplest function is called is multiplication. So if you have 2 matrices M and N, and for simplicity, let's just assume that they're both square matrices. They're both n by n square matrices. You can multiply them together to get a matrix P. In terms of indices, this is denoted as P sub ij equals, now you have M sub ik, N sub kj. So that's 2 different sets of components, and you multiply them together and you sum over all possible values of k. So that's the matrix multiplication. And once we define matrix multiplication, we can also add a fact, which is that if you take 2 matrices M and N, and you take their Hermitian conjugate, which is defined over here, this is equal to the Hermitian conjugates of the individual matrices multiplied in reverse. So this will be an important fact also that will show up later. Okay, now the final case I want to talk about is the so-called tensor product of matrices, or tensor products of objects in general, which we'll get to later. But if you have 2 matrices M and N that are both n by n square matrices, then the tensor product, which we can call Q, is an object with 4 indices. So each matrix has 2 indices that specify the entries at each pair of row and column, but the tensor product has 4 indices, and the value of the essentially the value of the entry at those four indices, specified by those four indices, is the product of the corresponding entries for the matrix M and the matrix N. It's important to note that M tensor product N is not the same thing as N tensor product M, because if we did that, then in terms of the matrix, if we look at the entries Q, I, J, K, L, in that case, it'd have to be Nij times MKL, which is not the same as Mij times NKL. Okay, so now that we've like gone through the review of all this, it's time to do something which is really interesting, which is to turn all those statements that we had before into diagrams. And these diagrams, in case you want to look this up later, they have several names. So I'll write down the names. So the first name is, they're often called tensor networks. They're often called Penrose diagrams or Penrose graphical notation. They're often referred to as bird tracks. And they're also often referred to as quantum circuits. Now, technically, each of these is slightly different and they have their own caveats, but for our purposes, these can all be essentially identified together. And now you'll notice that the name Penrose appears here, and whenever that appears, you know that you're in for an interesting adventure. So here we go. Okay, so the simplest thing that we can convert to a diagram is essentially the symbol M sub ij. It's a matrix. It has two indices. The diagrammatic symbol for this is represented as follows. So we first draw M in a box, and then we add two legs. We add an I leg and a J leg. For each index that the object has, we attach one leg that sort of sticks out from the box. Okay. Now suppose we have the matrix product of M and N. So that's given by this quantity over here. Well, if you look at the left-hand side, you have P sub ij that has an index I and an index J. And if you look at M appearing on the right-hand side, it has an index I and an index K. If you look at N, it also has an index K and it has an index J. The rule here is if you have two indices that are the same and that are being summed over, in terms of the diagrams, you actually connect those two lines together. So what we actually get in terms of diagrams is we join these guys together. So this is what it looks like. And also it's typical to not actually denote what the indices are on the sides here, and essentially just leave them blank. It can be inferred in principle from context. So here's another example. Suppose we want to find the trace of a matrix M. So how would we do this diagrammatically? Well, if we look at the right-hand side of this equation, we have two dangling legs. We have one with I, one with I. I'm not going to write those. And what we have is a sum over I. So what that tells us to do is it tells us to connect those two things together. So what we get this kind of loop where M is kind of like a bead inside of this wire, inside of this loop wire. As an example, suppose we wanted to calculate the trace of the identity matrix. Well, the identity matrix, first of all, has the property that if you take any matrix M and you multiply it with the identity matrix, then you get the same matrix M back. So I'll erase this in a second. But if you just look at this equation, then there's a choice for the identity matrix that you can make in terms of the diagrammatic notation, which is just to say that the identity matrix is just a straight line in terms of the diagram. It's just a straight line. And then diagrammatically, if you now attach this in place of the identity matrix, then you don't change, like just diagrammatically, you don't change the diagram because you just have continuation of the wire, which is the same as what you had before. So so putting this on the side, as an aside, whoops. That's gonna happen again. Okay, forget about that. So let's just scroll down a bit, and let's take this thing over here. The trace of the identity is now given by taking the identity, which is just a line, and connecting the two ends together. So what we have is we actually have a loop. That's what the trace of the identity is. And what is the trace of the identity? If the identity is an n by n square matrix, it's equal to n. So what we conclude from this is that diagrammatically, a loop should have the value of n. And this is a special case of a more general fact. If you have a picture, if you have a diagram where there's no, if there's no dangling legs, then that picture actually equals a number. In this case, it's equal to n. Okay, so that's pretty neat. So here's a slightly more complicated example. Imagine you have the tensor product of two matrices. It has 4 indices. So whatever this M tensor n diagram is going to be, it's going to have 4 things sticking out of it. On the right hand side, you have Mij and you have nkl. So all you do is your M gets an I and a J, and I'll stop denoting those things. So in principle, one of those is I, one of those is J. The N has a K and an L. And it's just that. It's just the concatenation essentially of the 2 diagrams together. So that's what the tensor product looks like in this diagrammatic notation. Now, there's an important thing to be aware of here, which is something it's something which we mentioned before as well, which is that the tensor product of M with N is not the same as the tensor product of N with M. So if you look at this diagram at a glance, it looks like, well, okay, what if you just switch M and N? Well, it looks like it's the same picture, but the fact that the tensor product is not interchangeable like this essentially means that whatever the top wire is connected to, it's possible to imagine the top wire as being connected to a fixed point, and the bottom wire is also being connected to a fixed point on both sides, and these fixed points are not allowed to move. So even if you switch M and N, if you hold these fixed points fixed, then the resulting diagram is not going to be the same as what you had before, because you're going to have some kind of tangling of the wires, if that makes sense. Okay, so now let's go through a slightly more complicated example. So this is the distributive property of the tensor product. If we take A plus B tensor C plus D, the distribution property tells us, it tells us that this is equal to A tensor C plus A tensor D plus B tensor C plus B tensor D. Okay, great. In terms of the diagrams, if we write this in terms of diagrams, it looks like this. A tensor C is just writing C down here, plus A tensor B here. Oh, sorry, this is A tensor D. So we have A tensor D plus B tensor C plus B tensor D. Okay. And now let's move on to a slightly different topic, but it's still in the realm of technically of linear algebra, which is the concept of the dot product and basis vectors. So any vector in a vector space can be expanded as a linear combination of some set of basis vectors in that vector space. If the vector space has a dot product, then we can choose basis vectors that are it's possible to choose basis vectors that are orthonormal, and that means that they satisfy this relation over here, bi dot bj equals delta ij, where this delta ij is the so-called Kronecker delta symbol. It just means that if I equals j, then the value is 1, and if I is not equal to j, then the value is 0. If we have this property, then we can actually calculate the components of a vector, the v sub i's, from the vector itself by taking the vector and taking the dot product with the ith basis vector. So given this, we can apply this now to a new space that we're going to introduce, which is the space of Hermitian matrices. So we defined Hermitian matrices before. The space of all n by n Hermitian matrices is itself a vector space, and that space has its own dot product. So if we imagine 2 Hermitian matrices A and B inside this space, then the dot product of those two Hermitian matrices is defined to be the trace of the product. So this is sort of the definition of a dot product. And diagrammatically, if we just go ahead and draw this out, well, A times B, that's contracting these guys, and we take the trace of the resulting thing that makes a loop over here. So so it's possible to just draw the diagram like that. Now, one choice of an orthonormal basis for this vector space consists of the so-called generalized Pauli matrices. So these are similar to Pauli matrices, but and if we consider 2 by 2 matrices, then they will be the Pauli matrices. But in general, they can be different. And if we choose basis vectors like this, then these Pauli matrices will. So I guess I can say that it's possible to choose matrices, sigma sub I, such that they, with respect to this dot product, they're orthonormal. Now, so when preparing this, I was confused about whether I should denote these as b sub i's or as sigma sub i's, because it's typical to denote basis vectors as with the letter b, and it's typical to denote Pauli matrices with the letter sigma. But then I noticed something. If you take a look at b versus sigma, it's obvious that there's a compromise that needs to be made, which is this over here. So from this point on, I'll denote these basis elements with this symbol, and instead of denoting the ith basis element with a subscript I, which is confusing because these are actually matrices, so they also have indices, I'll put the I inside of the circle. So at this point, what we can say is that any Hermitian matrix H can be expanded as a sum of it can be expanded as a linear combination of the sigma i's with coefficient ci. In a more general case, if we have an H which is Hermitian, but it's not just a single vector, it now has 4 of these prongs, then we can expand it as a linear combination of the tensor product of the sigma i's with sigma j's. Where at this point we have coefficients c sub I j, which carry 2 indices. So as an example, there's an important four-legged object that appears, which is called the swap operator. So the swap operator has 4 legs, and diagrammatically you can write it like this, but it's more common to write it like this. And what it does is it basically so it does 2 things. So first of all, it imagines that matrices are functions on vectors, and then things that have 4 legs can be thought of as functions on 2 pairs of vectors. And what it does is it basically swaps those 2 vectors. Quantum mechanically, because vectors can be corresponded with quantum states, what this essentially does, if it acts on a quantum system, is it switches the two quantum systems essentially. So it's a very handy notation, and as a consequence of the fact that it's Hermitian, you can express it as some linear combination of these sigma I tensor sigma j's with some coefficients c sub ij. So how do we find the c sub ij? Well, what we do is we take the vector, which is on the left hand side, and we take the dot product with the basis element. So we take the vector, that's this over here. We take the dot product with the basis element. Remember that a basis element is of this form: sigma I tensor sigma j. And what we do is we take the trace of the resulting thing. So how do we take the trace? So if you remember a while ago, the definition of a trace was basically you essentially take each index and contract it with itself. So here we have an index which we can contract with itself. Here we have an index which we can contract with itself. And this is the definition of. So in a sense, this gives you the c sub ij's. It's taking the dot product of a vector with the corresponding basis vector. Now, if you look at this picture, you can actually begin to see some interesting properties. So I won't derive like why this works, but the rule is you basically treat the sort of boxes as beads, and you treat the kind of curvy lines as like a wire that those beads can travel on, and then the diagram kind of speaks for itself. So how this works is you take this bottom box here, you can slide it along. You can slide it along the wire, and what you see happens here is that the wire it curves like this. So this box here actually becomes upside down, and that's important. But eventually, when it comes all the way around here and it goes to the other side, it turns right side up again. And then finally, we can drag it a little bit more and put it right next to the sigma I. So okay, this is getting a bit messy, but if we draw this more carefully, what this looks like is essentially we have sigma j. We have this thing. It's next to the sigma I, and then the whole thing is connected in a loop. But if you look at this, this is just the trace of sigma j times sigma I, which is the dot product of sigma j with sigma I. And because the sigma I is formed in an orthonormal basis, this is equal to delta ij. In other words, the Cij equals delta ij. That tells us that the swap operator here is it's just a sum over all I of sigma I tensored with sigma I itself. Okay. Now that we have this, we can notice something. So there's an equal sign in the middle. So this is very important. And incidentally, the fact that an equal sign is represented with two lines can get confusing because we have all these diagrams with all these lines over. But it turns out that you can actually interpret the equal sign in a very special way as being two lines that sort of connect the quantum circuits together. And if you ask a question about that at the end, I'll be happy to answer that. But so at this point, the fact that there's an equal sign means we can do something to the left side of the equation if we do the same thing to the right side of the equation. So here's what we're going to do. We're going to take the top right leg and we're going to connect it to the bottom left leg. We have to do the same thing then on the other side of the equation. So we connect these like this. What does this tell us? Well, on the left side of the equation, what we have is we have a straight line and we have a loop. Well, if you remember from a long time ago, the value of a loop was exactly n. So this is n times the straight line. This equals, well, now we can just straighten this diagram out. We have a sum over all I of the sigma I times the sigma I. So this will be important for later. Okay, so now that we have that, we're ready now, finally, to tackle the actual value of the integral. So here's how we do it. Here's the integral. We have the integral du of this quantity here. So now hopefully this integral makes a little bit more sense because we've defined what the thing in the middle is. The only property we need essentially is the fact that if you have the integral du of some function of u, then that equals the integral du of the function of u times an arbitrary unitary v. So this is equal to the integral du of, in the box here, u times v, and in the box here, u times v dagger. And so this is true for any unitary v. Now, if we use the properties from before, this is going to be equal to the integral du of u v, and the bottom here we're going to have v dagger because it gets reversed, u dagger. Okay, excellent. Now what we'll do is because this is true for any unitary v, we can choose v to be the following. We can choose v to be e to the power of I times epsilon times h, where h is some permission matrix, and epsilon is a very small number. If we Taylor expand this, then what we're essentially saying is that v is the identity plus I times epsilon times h plus something of order epsilon squared, which we're going to end up ignoring. So if we go ahead and plug this in, what this equation becomes is so this overall is equal to the integral du of u. And actually, before we get to that, there's one thing I want to do really quickly to simplify this. So if we look at this equation over here, we can actually slide the v dagger all the way to the left side of the integral sign. So if you like, this integral sign really has these lines going through it on both sides. We can take this v dagger all the way outside. We can put this v on like all the way to the other side, and then then on the inside, what we have is we have u on top and v dagger on bottom, and that's the definition of I. So this is equal to, on the bottom we have a v dagger, then we have the original integral I. On the top we have a v, and then we have nothing over here. Okay. So now that we have this, we can go ahead and we can plug in the expression that we have for v here. So what does that say? That says that this is equal to, well, so v dagger is going to be e to the minus I epsilon h. In other words, it's going to be the identity minus I epsilon h. So the identity minus I epsilon h in principle plus O of epsilon squared. all of this here. In the top, we have just the identity. Sorry, this is the original integral that we had. And then we get the exact same thing, just complex conjugated on the other side. So the identity plus I epsilon h plus O of epsilon squared. So this is what we have. Now we can use the rules of distributing tensor products to expand this out. And what this ends up equaling is, well, the first term is going to have an identity from the top and an identity from the bottom. So that's just going to be just the original integral I, because the identities are just straight wires. They don't do anything. Plus, now we'll have a term where we have the plus I epsilon h term from the top and the identity from the bottom. So that is plus I epsilon. We can factor that out from the entire diagram. We have the original integral. We have h up here. And then we'll also have a term where we have the minus I epsilon h from downstairs and the I from upstairs. That's going to give us, if we factor out the minus I epsilon h integral and nothing else. And finally, we'll have plus O epsilon squared. So that comes from all the remaining terms. And this, remember, if you follow the equal signs all the way back, we started with the original integral I, which, by the way, has 4 legs. So this whole thing equals the original integral I. We can cancel the i's on both sides of this equation then. What that tells us is that I epsilon times the original integral with an h over here minus an h downstairs, the original integral. This thing equals O of epsilon squared. We divide both sides by epsilon, by I epsilon even, then we cancel the square, and the left-hand side is independent of epsilon. The right-hand side is O of epsilon. So as we take epsilon to 0, this is going to become exactly 0. So what this implies is that this thing has to equal this thing. The integral with an h up here equals an h down here with the integral. Okay, now it's pretty easy to get lost here. The h is allowed to be any Hermitian matrix, which is n by n. So as an example, we can choose h to be one of the Pauli matrices, or we can choose h to be the generalization of the Pauli matrices. But before we do that, we can, because we have an equality here, we can multiply the left hand, we can multiply both sides of the equation by h in the bottom, and we'll do that for an interesting reason that we'll see in a second. So on the left hand side, we just stick an h there. We have an h still on the top. We have now 2 h's in the bottom here. We have I. And now, what we do is we set h to be sigma I, and we sum over all I. So when we do that, what we get is very interesting. So on the left-hand side, we have a sum over all I of a sigma I, the original integral, a sigma I over here. On the right-hand side, we have the same thing, where the h's are replaced by the sigma i's, and we sum over all I. But if you remember from before, we found that if we have a sum over I of sigma I and sigma I next to each other, that's equal to n times a straight line. So what that tells us is that we can just put in a straight line in the bottom with an extra factor of n. So we have this expression over here. Okay, finally, by some miracle, we've managed to isolate the original integral that we wanted on the right-hand side of the equation. Who knows how it got there, but it somehow did. On the left-hand side, we also have the original integral, but we have some junk there. Here's how we deal with the junk, and I think this is the reason ultimately why this calculation is really cool. So if you look at the junk, what you'll see is that there's a junk upstairs and there's junk downstairs. But we know from before that there's a case when the junk being upstairs and there's a case where the junk being upstairs and downstairs simultaneously gives us something that we know. So how can we arrange for the junk to be both upstairs and downstairs right next to each other? The trick is simply to move them in such a way that they are like that. So what we do is we write the left-hand side as the following. So we have a sum over I still. What we do is and I'll have to scroll a bit for this. So we have the original integral I, that's still there. And if you look at this picture, the top left and bottom right lines are just normal. But we want to take this junk, the bottom junk, and we can put it all the way down here. So that's where the bottom junk is. But of course it has to go in and it has to connect back. So it has to connect back, which is fine. But now let's take the top junk and let's also force the top junk to be right next to the bottom junk. So we take this guy and we force this wire all the way around here. Actually, let me redraw this because it looks really cool at the end. Okay, so let's give this guy a lot of room. This goes in there. This thing comes around and it goes like this. And we have another sigma I over here. And this, of course, has to go back, over, and out. So that's the final picture that we have. So so all we did is we just imagined that these wires are shapeable, and we simply move the things so that they're right on top of each other. And then we can use the fact that the sum over I of those things being right next to each other is simply a swap. So let's go ahead and plug that in. We can take this chunk here, delete that. Oh, shoot. Okay, that's not what we wanted. Okay, so we can redraw this. And what we have is, okay, you just have to trust me on this. We have the original integral. The top left and bottom right are fine. We have this thing over here, which goes all the way down. And you see that when it goes down here, we need to make it go up here. Maybe I can do this with a different color. So this has to go over here, and this has to go down here. So that's an identity that we derived before. If we do that, what we essentially find, if we follow this, if we follow the red lines all the way around, is that we go down like this, we go up here, and we escape from the top. So the line from the bottom essentially is it's essentially going to escape through the top, like that. On the other hand, if we look at the remaining line, let's do this in green. Let's use this green. So this line over here comes around like this, goes down here, and it crosses down here, but then it goes around and it comes right back into the bottom left corner somehow. So what we have is that this thing is connected. Let me undo this. Is somehow connected to that one over there. So somehow this entire tangled mess simplified into this. Finally, we can plug in what we originally knew about the integral. So what we have is that the integral is the integral du of u up here, u dagger down here. The top left and bottom right things are fine. And then what we have is we have this thing getting plugged into itself. So we have this getting plugged into itself. We also have like an extra line just somehow existing. So this thing is going around like this, and it comes out and it exits through the top. Now it's possible to once again slide the beads across the wire. So if we go ahead and slide this u across the wire, well, first of all, there's a curve here, so u turns upside down. But magically, and so if it just turned upside down once, it would be disaster, because we can't cancel it with u dagger then, because they're not facing the same direction. But when it goes through the wire, it turns back around, and then we have u times u dagger, which, because u is unitary, they cancel out. So as a consequence, what we have, this entire thing equals just the integral du. So that's still there, but we have this thing here, and if we follow the entire trajectory, it exits through the bottom, and then this thing, which starts at the bottom, exits through the top. So we have this over here. Now so at this point, we have the integral of du of just a constant, and the integral of du then is just the volume of essentially of the space of unitary matrices. It's just going to be some constant. We don't really care. We don't really care that much about it. Some people just set it equal to 1 because it's kind of a matter of convention. We can set it equal to 1 here if we want, and what we have is just simply the swap. But if you remember correctly, this is not exactly the original integral, because if we follow the equal signs all the way back, this was all the way. Sorry, where is the last equal sign? Over here. That's what this was over here. So this is n times that original integral. Finally, we can solve for the integral. We find that the integral du of u tensor u dagger is 1 over n. And okay, I use the equal signs once again. 1 over n times the swap. Okay, and that concludes the calculation. And I guess we don't have time to say anything else. Yes. So if there are any questions, let me know.
I have a question. So what does that mean?
Oh,
1 over n times the swap. And
good
why
question.
was this interesting for calculating this integral?
So one of the things that it means is that if you somehow had a really powerful, so imagine you and your friend had a quantum computer. Each of you has a different quantum computer, and imagine that by some force of nature, acted by the sum of this thing on your and your friend's quantum computers, then it would swap the states of the quantum computers. Now, acting by this kind of thing is actually really difficult. Instead, or a more reasonable application of this particular integral is to imagine what happens if you have a quantum state, a single quantum state, and do something random to it. Where something random means essentially that you don't know what would happen to it. Then, in principle, if you don't know what happened to the state that you just had, that could be it could be any state. That's one of the consequences of this result. It mathematically proves it. In general, the generalization of this essentially involves calculating these kinds of integrals for arbitrary circuits, and if you can do that, then it turns out that there are there's a whole range of physical applications for that, which I can go into if someone has questions about that. But I can stop the answer there for now.
Other people have questions in the audience or the online audience?
Yeah.
So these lines are formally called end boxes or Penrose diagrams. Is that correct?
So you can call them. So there are many names. Some people even call them Feynman diagrams.
Okay.
But I think quantum circuits is probably the most accurate in this case.
All right, then if there's no other questions, let's thank our speaker one more time. And once again, everyone here, if you haven't signed in yet, please sign in. Thanks for the road, but yeah, hopefully we can see you all next week. And you'll be around if you have any questions. Well.